Dzień dobry. Szanowni Państwo, witam wszystkich na serii webinarów o nowych technologiach Wiedza ma warstwy. Jest to już trzecia edycja. Zapowiada się bardzo ciekawie, czeka nas sporo ciekawych spotkań z liderami na rynku nowych technologii, a dzisiejsze spotkanie będzie prowadzone w języku angielskim. Będzie ono podzielone na dwa tematy i po każdym zrobimy serię zadawania pytań. Także zachęcam pisać pytania na czacie, albo jeśli będą chcieli Państwo zabrać głos, proszę też zgłosić taką chęć na czacie, wtedy dopuszczę Państwa do mikrofonu. Okay, we'll continue in English. So, welcome everyone once again in our webinar series, Knowledge Has Layers. As I mentioned in Polish, we will have two rounds of Q&A. So feel free to write your questions in the chat, or if you want to ask it out loud, please write on the chat that you want to take the mic, and I'll let you do that when the time will come during our Q&A session. Please, during the presentation, mute your microphones. And yeah. Now to the most important part. Today we have a very interesting guest from LS Instruments. It is very nice to meet you, Colleen, Dr. Colleen Brett. So the floor is yours.
Thank you very much, Anna, for the introduction, and thank you everyone for joining this webinar today. It's a great pleasure for me to talk about advanced light scattering techniques. And let me start actually right away. So we're talking about light scattering techniques, and we're talking about materials, novel materials, biomaterials, and their characterization. This belongs in the soft matter field. And when we're interested in characterizing these kinds of materials, we're looking at polymers, molecules, proteins, emulsion droplets, surfactants, many different types of systems that fall in the nanometer range and sometimes also in the micrometer range. To characterize these materials, there are several techniques available, among them microscopy, neutron scattering, centrifugation, or laser diffraction, for example. Now, when we look at microscopy techniques, like electron microscopy or AFM, for example, I think we all know that these techniques are rather expensive and also require quite a lot of sample preparation. And this is where light scattering can really help for characterizing materials and biomaterials in the nano world. So when we look at light scattering technology, we choose it as a characterization method because first, the sample preparation is rather easy. We can do fast and simple measurements. So it's really just loading a sample in a cuvette, loading the cuvette in a device, and then starting a measurement, which is about 1 or 2 minutes. The approach with light scattering is non-destructive. There's no deformation of the sample. There's no burning of the sample. It's also in situ because you're observing what happens at the sample at this moment. And it's also very powerful because you can obtain several parameters from it: size, shape, molecular weight, viscoelasticity, turbidity, diffusion. There's many parameters that can be obtained. And there's two main applications of light scattering that I want to talk about today. The first one covers the measuring of particle size and shape, which one would do with dynamic and static light scattering, also called DLS and SLS. One can also use light scattering to determine the microstructure, diffusion of particles inside a sample, and probing its viscoelastic properties, effectively conducting contact-free rheology. And I will talk about this in the second part of this presentation. So I will start first with modulated 3D dynamic light scattering and how to perform accurate particle sizing. So when we do dynamic light scattering or static light scattering, what we do is that we send a laser beam onto the sample. The sample consists of nano or microparticles in suspension in a solvent. And there are some dynamics of these particles because they are agitated by thermal motion. They are undergoing Brownian motion given their size. And when the laser beam goes through the sample, it is scattered by the particles in the suspension. And these, when we look at dynamic light scattering, we're looking at the dynamics of these fluctuations. So the light that is scattered will fluctuate according to the motion of the particles in the sample. We harvest these light that is scattered using a photodetector connected to a correlator. We get the raw signal, that is the intensity versus time, and this represents already the dynamics of the sample. The faster the fluctuations are, the faster the dynamics of the sample are, and so typically the smaller the particles. On the contrary, if you have large fluctuations, like longer time fluctuations in this pattern, that means that the particles are slower, that the diffusion is slower, and that the particles typically are bigger, larger. So already from the intensity fluctuations, you can get an idea of the dynamics of the sample. In DLS, what we do is that we take these intensity fluctuations, compute the correlation function from them, which tells us how fast, again, the dynamics are, how fast the correlation function decays. If the correlation function has a very fast decay, it means that the particles are rather small. And if we see a slow decay, it means that the particles are rather large. And this, fitting to an appropriate algorithm, can help us obtain the particle size distribution, which gives us the average value for the radius of the particles and the polydispersity. Because of course, in a real-world sample, you don't have only one type of particles that's, for example, 50 nanometers, you might have 55 nanometers, 45 nanometers, and there's a distribution of that size around the mean value. Now, what I've said for DLS is valid only if we look at signal scattering, which is what happened when we measure a dilute sample. So in this case of a dilute sample, we have particles that are sufficiently apart from each other that every photon coming into the sample is scattered only by one particle. If we have a concentrated sample, we see that the photons that arrive in that sample can be scattered by multiple particles. And that is a problem in DLS because it means that the angle at which we detect the light scattered is no longer the real scattering angle of the particle. And this basically produces errors in the results that are hindering DLS as a technique in general. So if you have done DLS in the past, you know that typically you are restricted to measure dilute samples. And again, as I said, the challenge is that then when you want to reach higher concentrations, again, you have to dilute. So you are modifying the properties of the sample. You, of course, induce a preparation step, which is not desirable when one wants to conduct many different characterizations, when you have many samples to measure. And also, it's difficult to know when the degree of dilution is sufficient. People typically do it by eye, but they have to try several times measuring the sample to make sure that they get the same results. All in all, the fact that you have these undetectable and systematic errors at a certain concentration is extremely inconvenient and typically goes underseen by users. So we do see that people doing dynamic light scattering typically have errors in the measurements, and that has led to light scattering being, you know, an undervalued technique in the characterization of nanomaterials. To solve this problem, LS Instruments has created a technology called modulated 3D dynamic light scattering, which is an improvement of an already existing technique that was invented in the 90s, which is called 3D light scattering. And what we do is that we suppress multiple light scattering with this technique. Allow me to explain how this works. We basically use two dynamic light scattering experiments instead of one. So you see two laser beams here arriving in the sample, crossing here, defining a certain sample volume. And then you have two channels. So you're going to harvest the light scattered on channel A and on channel B using two different detectors. What is important to know is that in both channels, when the sample is concentrated, you're going to have a part of the signal that corresponds to single scattering, and you're also going to have a multiple scattering component. So you are going to have some photons that have been scattered by one particle, and you're going to have photons that have been scattered by multiple particles. And that is, of course, when the sample is concentrated, but not too much also, because you don't want to have only multiple light scattering. And you have this in both channels, so single scattering plus multiple scattering. What's important to know is that since you're making the beams cross, you're defining the same sample volume in each channel. And the single scattering information is going to be the same across both channels, while the multiple light scattering information is going to be a random component of the signal. So by comparing, or better saying, cross-correlating the signal among the two channels, you can identify the random components and effectively eliminate this multiple scattering component. And what you get as a result is the single scattering signal. So basically, 3D light scattering is a way to filter out multiple light scattering. And that is what we use to make sure that we have reliable DLS measurements. And this is how it looks like implemented in a light scattering device. So we use a beam splitter, an optical component that can split the laser beam into two components of equal intensity. Using a system of mirror, we can create two laser beams that are parallel, and then using the lens, we focus the two beams inside the sample. And as I said before, we have then two photon detectors, and our correlator perform cross-correlation. Now, when you do this 3D cross-correlation, there is one drawback in this, is that you have a reduced signal. This is the kind of signal that you would obtain in standard DLS. The intercept, the value at which the correlation function crosses the vertical axis, is close to 1, which defines ideal signal, high signal-to-noise ratio. There is sufficient multiple light scattering events, and also the sample is not too dilute. Now, when you do 3D cross-correlation, because you perform these two light scattering experiments at the same time, you're going to have crosstalk between detectors, which means that this multiple light scattering adds to the noisy background. And also here, because of this crosstalk, you get this reduced intercept, basically. So you start with a low signal. And as I said, when you have multiple light scattering, you have noise on top. And so the intercept, so the cross-correlation function, is going to decay to be very, very small, and it's going to be difficult sometimes to fit data if you're measuring on very concentrated samples. To counter this drawback, at the LS Instruments, we have developed a technique that consists of rapidly switching between the two channels using acousto-optic modulators. So one laser beam is switched on, one is off. In doing so, we don't have this simultaneous two channels coming to the detector, and we can effectively suppress multiple light scattering while keeping a high signal. And this is what we have in standard DLS. Again, we have high signal. In 3D cross-correlation, we have accuracy, but somewhat low signal. And when we have modulated 3D cross-correlation, we have high signal and accuracy. This is very important to consider. If I look here at the results that were published in this reference paper here, I see that the sample, when it's dilute, so when the transmission is rather high, the results in terms of size obtained from a particular sample are the same when we look at the dilute regime. However, as we increase the concentration, so we decrease the transmission, you see that the size that is detected by standard DLS is completely inaccurate. We're going to see errors up to 60%. When we use 3D dynamic light scattering, you see that the size that you measure stays the same among the transmission measured, so among the concentration measured. The difference between 3D cross-correlation in its basic implementation and modulated 3D cross-correlation is the precision that you have on the results. So both of these methods are accurate, but you have a higher precision using modulated 3D. For the user, this basically means that you can do faster measurements. Typically, to reduce such an error bar here, one would need to conduct longer measurement to ensure that you have higher signal acquired, you have higher statistics, that reduces these errors that you can see here. In modulated 3D, you start with a high signal, so the accuracy and the precision are high, which allow you to do relatively fast measurements. And we have shown this also using a suspension of polystyrene in water. So polystyrene at a diameter of about 132 is a typical size that one will also investigate when developing new materials. And we've compared the results that we have using our technology and using a real standard DLS particle sizer. And again, here you can see that as a function of the volume fraction, when we increase the concentration, so at low concentration, you start with the same values measured. And at high concentrations, you see that the size that you detect is completely different from the expected nominal size. On the contrary, when using modulated 3D light scattering, you see that the size around the range of concentration measured stays the same. So you have errors that are appearing at high volume fractions with standard DLS, which we don't see in modulated 3D light scattering. And so this was basically the first part here, and I think it's nice now to stop for a quick Q&A session. If you guys have questions, I'm very happy to take them, and I'm also happy to provide further reading on this technique.
Yes, please feel free to ask questions on the chat, and answering the first one, which is a bit more directed to me. Yeah, we will share the whole recording. So if you were registered here, so we will get it on your mail. If anyone wants to ask question out loud, please let me know. This is the right time. Yeah, if you want, you can switch on your microphone, please.
Hello, thank you very much for this background that you provided us. At the beginning, I thought that it's important that the lasers illuminate the same volume of the sample at the same time and you analyze it, let's say, simultaneously. While in the modulated version, you have some time shift, so there is, certainly not the same particle is illuminated in the volume. It doesn't matter anymore for the analysis?
So typically, when we use this switching, it's extremely fast. We're talking about something like 800 nanoseconds of switching time. So typically, the dynamics that we will see are the same. Like the sample does not decay typically fast enough to not consider it's not the same scattering volume. So we don't have a problem in this case because the switching is extremely fast.
Okay, I get this approximation. Thank you.
No problem. Should I continue on the second part?
I guess, yes, maybe if someone will have questions to the first part later, you will answer them to later.
Of course, of course.
Let's move on.
Okay. So let me continue then with diffusing wave spectroscopy and how to conduct contact-free and high-frequency rheology, also a large application of light scattering. So when we do rheology, we're basically looking to characterize the viscoelastic properties of a sample. And the most known way of doing this is to conduct mechanical rheology experiments where we load a sample in a rheometer, typically in a geometry like this, where we have a cone and a plate, and we're going to deform the sample and analyze the response to that sample of the external deformation. Basically, this constitutes a very destructive method that is not always desired, especially when working on materials that do not have high viscoelastic moduli, when you're working with rather brittle materials. So another way to conduct rheology is to do microrheology, where what does one do is to probe the motion of embedded particles in the material. So you have these particles, and they're also moving with Brownian motion, which basically means there's no external forces applied. You also have this contact-free approach, and we have no evaporation going on in the sample because we measured in sealed cuvettes, which is not always the case in a rheometer. There are several ways of conducting microrheology experiments. The first one is to do video tracking, which you can do with a microscope, for example. You can also use DLS to perform microrheology with a somewhat restricted frequency range. And you can also do DWS, diffusing wave spectroscopy, which I'm going to talk about in this presentation. The main advantages of this technique is the fact that you probe a broad frequency range, that the sample volume that you probe is rather large compared to DLS. So in DLS, you probe a very small, in the orders of micrometer range volume here. And in DWS, the size of the laser beam is expanded to about 1 centimeter. So you can probe an area that is much larger. It requires minimal sample preparation, and low sample volume also are involved. And it's also a fast technique that doesn't need a lot of sample preparation compared to video tracking. So let me show you a little bit more when we talk about frequency range. This is the frequency range in rheology that the mechanical wavemeter would analyze, and it typically goes up to 100 radians per second. In DLS, you would cover roughly the same frequency range, although with a little bit higher upper limits and lower upper-lower limits. And also the amplitude of the modulate that you're going to record is a little bit lower too, which means that you cannot probe highly viscoelastic samples. In the ECODWS implementation, what we do is that we can measure at very, very high frequencies and on very comparable moduli range as in a mechanical wavemeter. So this provides a way to probe higher frequencies in rheology, which is especially useful when one wants to characterize, for example, the jetability of inks or the behavior of surfactants at these relevant concentrations, frequencies. And so what I was talking about earlier with DLS, we saw this picture here of several samples. This one is very dilute, this one is very concentrated, and this is what standard DLS would typically be able to measure reliably. We can use modulated 3D DLS to measure extremely concentrated samples without having to dilute them. And in DWS, it's very different because here we tried to measure single scattering and we wanted to suppress multiple light scattering. However, in DWS, what we are looking to do is to investigate samples that are concentrated. We want actually to probe concentrated samples that are opaque, because what we are looking to analyze is effectively multiple light scattering. So what we do is we probe again the motion of particles that are embedded in the sample to obtain information on the dynamics of the matrix in which the particles are embedded. And these particles, they can be naturally present in the sample, like, for example, droplets in an emulsion or particles in a suspension. And if the sample is not naturally turbid, if you're looking to characterize a sample like this and you want to perform contact-free rheology measurements on them, you can also add tracer particles to the sample to make it turbid. So effectively, DWS can also characterize transparent sample, provided that you add tracer particles. In such cases, one would typically use titania particle or polystyrene particles, depending on the physical-chemical properties of the sample. And to explain a little bit better how this technique works, we have also here a laser beam that is sent onto the sample. And in this case, we're looking to characterize the dynamics of photons that have been scattered multiple times in this sample here. And so what we're looking at here is the random walk of a photon within the sample, given a certain cuvette size. There are two quantities that we need to define in order to be able to perform our analysis. The first one is the mean free scattering path, which is effectively the average distance between particles, so the average distance traveled by a photon before it's scattered by a particle in the sample. Another very, very important quantity that we want to get is the transport mean free path, which is the average distance that the photon goes through in the sample before its propagation direction is randomized. So we're looking really here at random motion. And the L star here is basically a measure of the turbidity. Because if you consider a more concentrated sample, you see that the L, the mean free scattering path here is going to be smaller, and so will the L star. So L star is basically proportional to the inverse of the turbidity in the sample. Then when the photons exit the sample here in the transmission mode, again, we're going to analyze the scattered light by the sample, and we're going to focus here on a single speckle. So we're going to look at this zone and check how does light fluctuate as a function of time. So this is what we do here. So we get the intensity fluctuations, intensity versus time. In a similar way to DLS, we're going to compute the intensity correlation function. Now, importantly, in this intensity correlation function, there is multiple light scattering information, which is what we want to get from the DWS. And again, how fast the particles diffuse tell us how, here in this case, how viscous or not the sample is. If the particles can diffuse rather fast, it means that the sample is not so viscous, that you have low viscoelasticity. And if the particles, if the motion here has a slow decay, which means that we have some kind of thick, very firm sample in which the viscoelasticity is high. So this is really to get a feel of what we're looking at in the correlation function. We're looking at a bulk analysis at multiple scattering. So in this case, we don't get an average particle size, but we can get the mean squared displacement of the particle, which is an averaged value, of course. This tells us how free the particles are to diffuse in the sample. And typically for a purely viscous sample in which there is no elasticity, we will see a linear behavior. So the particles diffuse with time unrestricted. Then it's important to know that to go from the correlation function to the mean square displacement, the sample should have an ideal turbidity, which means that the size of the cuvette divided by the L star should be between 5 and 40, which means that the turbidity should be within a certain value. The sample should not be too opaque. We should have a sufficient signal that exits the cuvette here. And the sample should be turbid enough that we only look at multiple scattering. If you're not within this condition, you can adjust the cell width, so you can use a smaller cuvette, or you can also increase the tracer concentration, for example. And in typical equipment that people would use, the device basically calculates this value and tells the user the sample is okay to be measured, or the sample is not turbid enough or too turbid. So this is done automatically. Then this basically constitutes the basic analysis of DWS. So this is the principle. From DWS, we can get microrheology information, provided that we know what is the particle radius in the sample, which can be known because we add tracers or because you've measured, for example, this particle radius using DLS or another technique, in which case we get the same quantities as in classical rheometry, so the viscous and elastic modulus. It's also possible, if your sample is purely viscous, if there is no elasticity, to do particle sizing with WS, but this will be done on a somewhat restricted range from 100 nanometers to about 1 micron. In comparison, in DLS, we're investigating sizes between fractions of a nanometer to about 5 microns. So this is the main difference in particle sizing. In DLS, you look at a broader size range. But it's useful to have a device that can do, two-in-one analysis, especially when you look at emulsions, for example. And so I want to expand a little bit more on the principle of DWS microbiology. So there's two main cases that we can look at. The first one being the case of a Newtonian liquid, where the particles are free to diffuse within the solvents, in which case we're going to see a correlation function that decays to 0, and a mean square displacement that is linear. This means, again, whatever the time that we probe the sample at, the particles are not restricted. They can diffuse however they want, so the motion is basically linear here. This means that we can extract a diffusion coefficient looking at the slope of this curve, and using the Stokes-Einstein equation, we can compute either the viscosity or the size of the particles, knowing, again, the slope of that curve. If we look then at a viscoelastic sample, we're going to see a very different behavior here. We have particles that can somewhat diffuse, but at some point they're going to be trapped in the viscoelasticity of the sample. So let's take, for example, the case of, for example, yogurt, where you start from pure milk, which is a liquid, in which case particles can freely diffuse. When the yogurt, for example, starts to form, you have a gel network forming in the sample that restricts the displacement of the particles. So they can only move within a certain amplitude. There is a Kelvin element present in the system. When that is the case, we're going to see a decay of the correlation function that has a certain baseline here. So the correlation function never decays entirely to 0. And most importantly, what we can see is that the mean square displacement shows a slowdown and often a plateau at high lag times, which means that the particles can diffuse, but only with a certain amplitude. And after a certain amplitude, they're kind of meeting the cages present in the network, and they're trapped. They cannot go further than this. And this is how we can see directly if we are looking at a viscoelastic sample or at a purely viscous sample. When that is the case, we can apply the generalized Stokes-Einstein equation to the mean square displacement, and from it we can extract the elastic and the viscous modulus here. I wanted to provide an example of such gelation monitoring, for example. Here we were working with a pea protein solution on which we wanted to record a gelation behavior. We know that pea protein solutions typically gel at high temperatures, around 80 degrees, and this is what we probed basically here. So we used the pea protein solution with a concentration of 15% in weight per volume, and they were suspended in a buffer, PBS, and then we increased the temperature from 20 degrees to 80 degrees by steps of about 2 degrees. And what we are really probing here is the viscoelasticity, but also the microstructure of the protein solution. And we can directly see this with the mean square displacement curves, because when we look at temperatures below 74.5, we see, again, a linear behavior with particles present in the pea protein solution that are free to diffuse. And after a certain temperature here, we see that the behavior dramatically changes with time. So you see that for the 76.5 temperature considered, the mean square displacement shows an increase, again, linear at low lag times. And at large lag times, you see this very strong plateau present here, which means that the particles, again, are trapped within the gel network formed by the pea protein solution at this temperature. So you're basically able to record a gelation process in the sample, but you can also, of course, observe different kinds of process like polymerization, aggregation, looking also at DWS data. And so again, here at low temperatures, there's no microstructure, and at large temperatures, you have strong microstructures present in the pea protein solution. The same kind of behavior can be observed with kappa-carrageenan, for example, which is a quite famous gelling, thickener, and emulsifying agent in the food and pharmaceutical industry. And here we know that kappa-carrageenan only gels at certain temperature if we introduce cations in the mixture. So we use KCl solution here, and we mix the kappa-carrageenan with the same concentration in this sample. We added tracer particles to that one, so with a diameter of about 500 nanometers. And in this case, kappa is a sample that does not gel at high concentration, but at large temperatures, but at lower temperatures. So in this case, we submitted it to a decreasing temperature range starting from 60 degrees and ending at 24 degrees. And again, what we can see here is a very sharp microstructural change between 4 degrees and 38 degrees, where the sample goes from linear behavior and here critical gel state to a fully gel state in which we see a strong nonlinear behavior and the formation of a plateau. The difference in the case of kappa-carrageenan is that you see a further increase at larger lag times, which can be basically interpreted as the fact that after a certain lag time, the gel network in kappa-carrageenan sort of relaxes to let the particles motion happen again at a certain lag time here. And I want to precise also that each of these measurements that we see, each of these curves, they take about 1 minute to be acquired, and you can really span the full frequency range at once, contrary to what you can do with a mechanical rheometer. We can see this more closely by looking at here pure rheological quantities. So people would typically look at the G prime, double prime, which we show here between 4 degrees and 38 degrees, where you can really appreciate the difference in behavior observed. So we go from a state where we almost have a gel. We see that the loss tangent here is very, very close to 1. And at 38 degrees, you have this very sharp change in the behavior of kappa-carrageenan and the crossing of the viscoelastic moduli at a certain frequency, which, by the way, is not visible in classical rheometry. So this is the maximum frequency you could observe in classical rheometry, but here you can really see that there is a crossing of the moduli at this frequency. And we like here to look at the loss tangent, which is just the comparison of G double prime versus G prime, where you can really see at which point you have a crossing of these two quantities, which typically defines where you can identify a gelation monitoring process. I wanted to provide some examples here related to 3D bioprinting, which is one of the most active fields when developing biomaterials. And here we look at 3D powder printing, which is a nice application for biomedical implant manufacturing. And what people are typically looking to do in this field is to control the polymerization process, and in particular the interactions between the powder and the ink present in this process. And with DWS, what we can do is basically record the polymerization process in situ. And this is a paper that was published by some of our customers, where they really studied this in situ polymerization looking at DWS. And in that case, you could even look only at the correlation function. The changes induced in this material were directly recorded with the raw data of DWS. And so that is an example of, again, 3D printing of biomaterials. Of course, this also applies to non-biomaterials and can apply to a wide range of techniques here. Another example that I wanted to show is the example of 4D printing, where people look at developing materials that can be 3D printed, but that also have temporal dependent behavior, like biodegradability. For example, materials that will be present at some point in the human body, they have to be degradable within some conditions. And also materials that have shape memory. And the current focus, of course, because on the long term, these materials need to be implemented in human bodies. A focus is to make these formulations biocompatible, and that often means removing sulfates in the formulations. And here again, DWS can really help to characterize mechanical properties of polymer resins, because you're looking at a technique that can characterize samples that are sealed relatively fast and non-evaporation behavior, and also at large frequencies. So this is another paper that was published by some customers of ours in the US that you can take also as reference to 4D printing of biomaterials. And at this point, I'm also happy to take questions on the technique and to discuss a little bit more about some other applications that you may be thinking about in DWS.
Yes, thank you. Once again, feel free to write your questions on the chat, or write in the chat if you want to ask a question out loud, live. I have a question, maybe more informative. So if anyone will have more specialistic question later, can they write to your email? And
of course, yeah, of course. This is you're all welcome. This is of course a lot of information at once, and I'm very happy to take questions by email. I think it's in the last slide. Yes. So I'm just going to leave that slide open here. And there's a lot of information that can be found on your website, the website of Cygnus, and the website of LS Instrument as well. So if anyone has questions about the techniques we mentioned here, so dynamic light scattering to characterize native sample without dilution, or DWS to characterize the viscosity and elasticity of samples with much higher flexibility than mechanical rheology, I'm very happy to take questions at a later point too.
Okay, so I think we will finish now. Thank you everyone for joining us. Thank you, Colin, for sharing your knowledge and for your presentation. This was very interesting. And I want to welcome everyone to the next webinar, which will start at 12 o'clock. Feel free to visit our website to see what will wait for you. Yes, if you will have questions about this presentation, please feel free to contact me. Via mail, you get the link to the webinar, or to Colin with the questions about your presentation directly. So yeah, thank you so much. Thank you for participation. Big thanks to our speaker. That was a pleasure. Have a nice day, and see you on the next webinars.